Today, we'll be talking a little bit about the, I called it regression as a distributional model. And what I mean by that is some of the stuff that Gelman and Jennifer Hill are talking about in their data analysis using applied regression book. So today, the things that we'll be covering are two main things. So first off, what do I mean when I say regression as a distributional model? And then I want to talk about the linear probability model. And then if we have time, the logit model. Okay? So those are going to be the three things that we're talking about today. And if I can get through all of them, that's great. My main point, though, is going to try and be to get you to a point where covering one and a little bit of two, you can complete the lab if you do the reading. So, assuming that everybody is good from here and there's nothing in the reading that we need to clarify, I'm going to proceed. Starting off with regression as a distributional model. In section 2.1 and 2.2 of the Gelman book, he talks a little bit about statistical distributions. And a distribution is just a characterization of the outcomes of a random variable. So I'm going to say characterization of outcomes of a random variable. So that kind of pushes the definition back to what is a random variable. And a random variable is just a value that represents some fundamentally unknown or unknowable process that takes on a value when we observe it. Okay? So the last time in class, we talked a little bit about flipping coins. And we talked about representing the outcome of a bunch of coin flips as a sequence that maybe looked something like this. Where 1 means that we got heads and 0 means that we got tails. So in this language, this is a sequence, a set of observations of a bunch of random variables. We might denote x. So that would be x1, that would be x2, that would be x3, that would be x4, and so on until we get sort of x over n observations. Okay? So a random variable is one of these things, one of these outcomes, or it's all of these outcomes at the same time, and we're just collecting them together. So if I refer to this as x, then I'm referring to the whole set of random variables, this whole collection of observations. Okay? Now, random observations and random distributions can have very different shapes. So in that example, where we have a binary outcome, we could say that our variable exists in the set of values that are 0 and 1. So that just is fancy mathematical notation right here, which you may see elsewhere, to say this variable, this random variable, exists in the set of values that are 0 and 1. Okay? So there are a bunch of ways that we could model that random variable. But the most common one that's used in quite a few places and is discussed in the reading is called a Bernoulli distribution. And in a Bernoulli distribution, you have one parameter. The parameter is, well, we would write, if x is distributed as a Bernoulli distribution, you'd say x, and then I would put this little squiggly, or a tilde, as it's called. And I would write Bernoulli. And the Bernoulli distribution has one parameter, p, which is the probability that x is 1. So in a Bernoulli distribution, or a Bernoulli distributed random variable, where p is really close to 1, then more often than not, when I observe x, it's going to be 1. However, if my probability of x being 1 is really small, then when I observe x, it's more likely to be 0. So you can kind of think about this as x is what you observe, and the Bernoulli distribution is kind of the theoretical behavior over all of the things we observe or don't. It's like the idea about how we describe all of the potential outcomes of x. And in the Gelman reading, he talks about this. So x is a realization, and its distribution describes what types of realizations we're likely to observe. So the Bernoulli distribution is extremely simple. It just has x that takes on these values, and that's it. Now, another distribution that we've worked a lot with is the normal distribution. Josh asks, would p equals 0.5 mean that there's a 50-50 chance x will equal 1 or 0? Exactly. Josh, that's exactly right. So the normal distribution is a distribution we've worked with before. And the normal distribution, we might write something like another random variable, let's call it y, is distributed normally, and we just normally use an n to say normal. Sophie asks, is the Bernoulli distribution only for those with binary outcomes? Yep. So the Bernoulli distribution only models data that has values of 0 or 1. So a normal distribution is characterized by two parameters, and you've seen this before. It's characterized by a mean, which is typically written as mu, and it's characterized by a dispersion, typically written as sigma, or sigma squared. What this tells us is that when we observe y, it's going to take values that are close to mu, and exactly how close is governed by sigma squared. So when sigma squared is really small and we observe y over and over and over again, it'll be close to mu. By the way, just for the people that aren't good with Greek, this is mu, and this is sigma. Okay? So this is sometimes called a location parameter. Because it tells you where the normal distribution sits. And this is sometimes called a scale parameter because it tells you how wide the distribution is. Okay? And you all have seen this kind of thing before, and I don't really need to show you too much about it. So, you know, if I talk about things like a normal distribution might have, well, that's more of a Laplace distribution. A normal distribution might have a shape like that. And we know that that is its mu. And some function here is going to represent sigma. And that for the same mu, but a tighter sigma, my distribution might look like that. Or for a different mu and the same sigma, my distribution might look like that. So you guys are familiar with working with these kinds of things. Mu is the average in the Gaussian case, and sigma is the standard deviation in the Gaussian case. So this would be sigma 1, and then that would be like 1 and 1. So you're very familiar with that, right? Okay. So there's an interesting process that can connect a normal distribution to a gamma distribution. Sorry, not a gamma, to a Bernoulli distribution. And we'll get to that, the importance of that in a second. But imagine, for instance, we had a normal distribution centered on a mean mu. And I could say, if we observe yi less than mu, say, I don't know, a binary outcome, I is equal to 0. And if we observe yi greater than or equal to mu, say binary I is equal to 1. So you can connect distributions in interesting ways. If we simulate y as a function of mu, and we say that our binary outcome is 0 when y is below mu, but is 1 when y is greater than mu, then this is the same as saying B is distributed Bernoulli with a p of 0.5, because half the distribution lies that way and half the distribution lies that way. So we're just as likely to be 0 as we are 1. So by linking things like y to things like b, we can transform one distribution into another distribution. Does everybody see how that works? Just imagining if I had a bunch of y values, if they're below the mean, I might convert them into a binary outcome that takes on a value of 0. And if they're above the mean, I'll convert them into a value that takes on 1. So all I'm saying is that I can transform different variables into different distributions. Another great example might be, you know how like when you guys do linear regression on, sometimes you'll do like, you know, you'll say y is a function of x beta plus e for some covariates, and you see that y is really skewed. Sometimes students that have done the reading will model the log of y instead. And that actually transforms what might be called a log normal distribution into a normal distribution. So by using the log of an outcome, we can change the distribution as well. Anytime you apply a function to a random variable, you're changing its distribution. That's the point. So when you model the log of y, your model actually changes your distributional assumptions of what y is. Okay? So if y is distributed log normally, then you can transform it back to a different distribution. The point of this is to kind of get you thinking about distributions. And if you've done the reading, you've seen all these other kinds of distributions that can exist. And the reason why distributions are important is because regression is just a fancy way of specifying a normal distribution. Okay? What do I mean by that? So if I have a regression equation which says y is equal to x beta plus e, and let's assume for a moment that I've stuffed my intercept into x beta. Actually, we don't have to. I'll model that explicitly because that'll probably be clearer for you guys. So we have the model that you recognize as alpha plus x beta plus e. The condition that you all are familiar with at this point is that e has to be independent, identically distributed, normal. So this is actually an explicit model of the distribution of your regression error. It says that for every observation, it needs to be normally distributed with a mean of 0 and some variance, sigma squared. Okay? So if that's true, then I'm going to rewrite my equation here and replace E with that distribution. So I'm going to write y is equal to alpha plus x beta plus some normally distributed value with a mean of 0 and a variance of sigma squared. So all I've done is I've written that out now as its distribution. Because E is just a random variable that every time we estimate a regression takes a value, and that value is normally distributed. So every time you see the distribution, you can replace it with the term and vice versa. Well, there's an interesting property of normal distributions. If my normal distribution is here, with a mean of mu, then if I add a value to mu, it just shifts the normal distribution up or down. It doesn't change the variance. This is a property of normal distributions that derives from them being what's called a location scale distribution. You can change the location of a normal distribution by adding a constant to all of its values. So, this means that when I can write y is equal to alpha plus x beta plus this normal distribution, I might say y is equal to x beta plus a normal distribution with a mean of alpha and a variance of sigma squared. Because alpha is just a constant. Alpha just applies to all of the different values. Okay? So it's just a constant, it's just a single value that applies everywhere. And we can add it into that distribution because it's a location scale distribution. Now the very last realization is that x beta changes for every x value, right? So if this is a single observation, xi might be, 5, but beta is constant for everybody. So this is going to be 5 times beta. This is going to be 7 times beta. This is going to be 9 times beta. So, because I can think of these things as a constant for any individual observation, where I can see x, I can then write y, and let's just say for a single observation, is going to be equal to a normally distributed value. Yeah, I'll get there. A normally distributed value where you have alpha plus x beta for the mean and sigma squared as your error term or your dispersion. And since now this is just a distribution, it's easier to recognize that yi is distributed with a mean of alpha plus x beta and a variance of sigma squared. So, Sophie, we go from line 2 to line 3 by recognizing that a normal distribution at some location, say M, can be shifted to a new location, let's say M plus A, by adding A to all of its realizations. So if I have a normal distribution with a mean of 0 and a variance of sigma squared, I can shift it to become a normal distribution with a mean of alpha by adding alpha to all of its realizations. This here you can think of as the distribution of alpha plus E together. Because alpha is just a constant, and E is still random, and E is still normally distributed. So if we add alpha to every E value, alpha to all the errors in our regression, then all we're doing is shifting the distribution of errors from 0 sigma squared to the distribution of this together at a mean of alpha. So that's how we're going from one to the other. I'll keep this here. So our errors have a mean of 0, and our alpha is a constant over all the observations. So when we add alpha to every error, that shifts the distribution but doesn't change anything else about it. And the last realization is that since each of the observations can be treated independently, I can add x beta to every observation, and even though that'll change, it'll still mean that the normal distribution applies. And so I've explained this before as the fact that when you fit a normal distribution over a set of points and you do a regression, what you're saying is that at a particular value of xi, there's actually a normal distribution of outcomes for yi. So just slicing in this narrow zone where things are basically equal to xi, I'm going to get a variety of yi that I have to model. That's part of the fundamental randomness inherent in linear regression. That just because say two observations have the same x, they're located at the same spot on the x-axis, they might be below the line or they might be above the line. So regression is about modeling the expectation of y. It's about modeling the mean of y when x changes. Because this is just a normal distribution for y. So when x is 0, we know that y is the intercept. But it could be above the intercept and it could be below the intercept. When x is 5, we know that it's going to be alpha plus x beta, but it could be above that or it could be below that. If sigma is really big, then this distribution will be really wide, and our point cloud might look like this. But the point is, regression is just a statement about a normal distribution at every single x value. Y is normally distributed with a mean of alpha plus x beta. That's all regression is about. Okay? So I'm going to erase this slide now so I can show you a little bit more about what I mean. You have seen that before, and I'm going to keep this up for a little bit. So if this is the regression equation stated as a distribution, right? We're saying that y is normally distributed at each point of x. So again, just to show you in the graphic here, what this says is that for any one value xi, there's a distribution of possible y responses. It's not just the line. There are going to be some errors around that line, and those errors have to be normally distributed. Okay? So, this describes the distribution of y at any x. And the language that you've seen in the book and the language that you'll see in the lab is that we're actually modeling this thing called the expected value of y given x. So this is called the expected value. And you can kind of think of it as an encouragement to take an average or, describe somehow your best guess of the thing that's on the left here. And this is read as, the vertical line is read as given, and then x. So regression is about building a guess for the value of y given that we've observed x. So that's all this means. The expected value of y given that we've seen x. That's what regression is about. The expected value of y given that we've seen x is alpha plus x beta. And there's some noise around that. It's a distribution, so the noise is sigma squared. The variance of that expectation is sigma squared. It's the uncertainty in that prediction. But that doesn't change the fact they're just making conditional expectations. Okay, so I'm going to erase that. So we denote that with this expectation operator. And linear regression is just about trying to predict the expected value of y. Okay? Now, instead of having a continuous y, like we have here, what if we just had a binary outcome of y? So to show you what that looks like, we might have where this is, let's just say 0 for clarity, and this is 1 for clarity. I might have a bunch of observations of y that are 1 down here, or 0 down there. Then I might have a couple of random ones up here that are also 1s. And then I might have a couple of other 1s up here and a few random 0s that happen. So you can think of this as, in the workbook, we're visiting a pub. And this is the waiting time in minutes that you wait for a pint. And your friend is judging whether or not this wait they consider to be too long. So 0 means, okay, wait. And 1 means too long a wait. Okay? So, our regression model that we use all the time still would assume that these things are normally distributed. And it all comes from the expectation for the error, right? That our error is normally distributed. But in this example, where y is binary, a fitted line is going to look something like this. So just drawing the line of best fit between a binary y and a linear x is going to give you something that looks like this. Okay? This is called a linear probability model. And what this means is that you're just doing a linear regression on a binary y. So do you remember how I was talking earlier where you might have a normal distribution and I might be, say, putting in a threshold t, and any y that I observe down here, I'll say are 0, have a binary indicator of 0, and any y that I observe up here, I'll say a binary indicator of 1. So it's just saying if I observe y, and y is smaller than t, some threshold, then I'll say it's probably a 0. And if I observe that outcome and it's larger than t, I'll say it's a 1. Okay? So the linear probability model still takes that normal distribution and tries to build an expected value for y. But it's going to predict all of these values continuous between 0 and 1. So let's say if I wait 6 minutes at a pub, then I'm going to get some value here of y that's greater than 0, but it's less than 1. This is why we call it the linear probability model. If you run a linear regression where your outcome is binary, the actual thing you're going to end up modeling is the probability that the observation is 0 or 1. Okay, so how this actually works is that you're modeling some binary outcome I, and that's defined as 1. Well, let's say it's defined as whether or not your y observation, which is a probability. I think in the lab, actually, the workbook, I use y to mean binary. So y is 0 and 1 with probability pi. So in this representation on our plot, instead of y, we'll say pi. Okay, so y is our binary, and pi is the probability that y is 0 or 1. So what the linear probability model, why not pi and just p? Pi does not represent 3.14 here. The reason why we use pi and not p is because pi is an unknown parameter. And normally in statistics, we use Greek letters to represent unknown parameters, like alpha up here and beta here. So pi does not represent 3.14 here. I'm just using it as to represent an unknown quantity that tells us the probability that y is 0 or 1. Okay? So we use pi because in statistics we tend to use Greek symbols to represent unknown quantities. And think about it. If all I observe is whether or not y is 0 or y is 1, there's no way for me to actually explicitly understand what pi is for any single observation. The probability is latent. It's not observed. All we observe are whether or not the wait was long. Okay? We'll get there, Noah. So in the linear probability model, as x increases, the probability y is 1 increases. So if we're waiting for 10 minutes at a pub, then this probability is going to be larger. So this is, let's call this probability 1, and we'll call this probability 2. This probability is going to be smaller than this probability. Okay? But the model is still only going to give you that fitted line. So in order for you to classify your predictions, we have to draw a threshold. We have to say, okay, at some value of P, we're going to say an observation is a 1. And at that same value of P, if it's smaller, we're going to say it's a 0. So the linear probability model says, okay, anytime our probability is greater than some threshold, y is going to be equal to 1. And anytime it's less than that threshold, y is less than 1. Okay? And all this just happens when you run a linear regression with x on a binary outcome y. Because of the thing that I showed you before, where a normally distributed variable can have a threshold placed and become Bernoulli, this linear probability model just works. It just operates. Now, I'm going to clear this slide, and then I'm going to redraw some stuff. Actually, I'm just going to move on because it's faster. So, again, representing our linear probability model, where I have a bunch of observations that are 0, jittering them a little bit for effect, and a bunch of 1s up here. And I fit the linear probability model. I still have the case that the alpha is the baseline probability that y is equal to 1. And beta is still the change in probability for y being equal to 1 when x increases by 1. So the linear probability model always works like this. Now, the tricky thing is that our predictions are going to be in terms of these probabilities, right? So if I predict at some x value 1, I'm going to get a probability that we can't observe that the observation is a 0. And I'm going to institute some threshold, maybe t, and I'm going to say, okay, any point on the line that's below there is going to get sent down to 0. And any point that's above that threshold is going to get sent up to 1. Does that make sense to everybody? So we're still going to make some errors. This point is going to have a large probability, but it's going to get predicted as if it's a 1. Its probability is still going to be something like pi 2, let's say. And there are other observations up here that are also x2, that are also pi 2, but that end up with y equal to 1. And that's because this model represents y as distributed Bernoulli pi I. And this just happens because you can take the normal distribution, chuck a threshold on it, and get the Bernoulli values out. Okay? So you can interpret alpha and beta in those terms. And in the assessment, I'm showing you that through using the linear probability model. Now there's an issue with this. If I get some really small x values, my probabilities can actually become negative. And if I get some really large x values, my probabilities can become greater than 1. The laws of probability suggest that it's only reasonable to talk about probabilities that are between 0 and 1. It doesn't make mathematical sense for there to be a negative chance of something happening. Nor does it make sense for you to have a greater than 100% chance of something happening. So the linear probability model works really well in some circumstances when you're trying to do these predictions inside of sort of an X range. And your predictions, if you get a negative probability, then you're pretty sure that it's below the threshold, and so it just gets assigned up to a 0. But keep in mind that the probabilities still aren't correct. So there's a different kind of model that's used, and instead of using a line, they use something else. I have a little bit of time, so I'll intro this just on its basics. So again, imagine we have yi being binary. It's either 0 or 1. Okay? So this might look like on a number line, a certain number of y are 0, and a certain number of y are 1. And then there's some implicit probability, which we're going to label pi, for that value. And that exists between 0 and 1. So on a number line, that's what our normal distribution is modeling. That's what our linear probability model thinks is normal. Okay? Now, in order to turn this into something that is useful for a linear model, we can do further transformations. So pi is a probability, and you can think of it as a percent chance of something happening. Something else that's used, particularly in betting and statistics, is something called an odds. And the odds are represented by the probability of something happening divided by the probability that it doesn't happen. So if an outcome is binary, pi is the probability that the thing happens, that it takes on a value of 1. And if a thing doesn't happen, then the probability of that occurring is 1 minus pi. Okay? So this is called the odds. And the odds, funky distribution. You can't have an odds smaller than 0 because pi I is always greater than 0. So you can't have a negative odds because pi I is greater than 0 and it's less than 1. So the numerator always is positive and the denominator is always positive. But it can go all the way out to infinity as a distribution. That's because as pi I gets close to 1, the denominator gets close to 0. So you get an increasingly large fraction between the two. So to think about it, if the odds are, if pi is equal to 0.5, the odds are going to be 0.5 divided by 0.5, which is 1. If pi is equal to 0.75, then the odds are going to be 0.75 divided by 0.25, which is 3. So as your probability of the event happening increases, your odds get bigger and bigger. Likewise, as they get smaller, your odds get smaller and smaller. So like if you say pi is 0.25, then this actually becomes 1/3. Okay? We're almost there. So if we recognize that the odds have this distribution between 0 and infinity, written like this, 0 and infinity, that's a really bad infinity. That's a better infinity. And we use a curly brace, or a curved brace, a parenthesis there, to indicate it can't actually ever get to infinity. If we have a distribution that goes from 0 to infinity, and there's a lot of kind of space between 0 and 1, which occurs when pi is less than 0.5, so the odds is equal to 1 or smaller, and then when pi is greater than 0.5, we're all the way out here. So we can go anywhere from 1 to infinity. To stretch that out and make it something that's amenable to a normal model, we model the log odds. So we take the log of pi I over 1 minus pi I. Now that exists in negative infinity to infinity. It's 0 when pi is equal to 0.5. And then as pi gets really, really, really big, the log odds gets close to infinity. So as pi gets close to 1, it goes to infinity. And as pi goes to 0, it goes to negative infinity. So the log odds can give us something where our distribution looks way more normal, even for really extreme values of pi. If we model the log odds of something happening using a normal distribution, you get a logistic regression. So the point here is that the linear probability model stops here. And the logistic regression transforms these probabilities into an odds ratio, and then again into the log odds. So by doing this, it stretches out the parts of the distribution that are close to 0 and close to 1, when probabilities are really big or really small. And then it keeps everything kind of close to a normal distribution, or kind of close to the original up here, when probabilities are close to 0.5. Functionally, this means that the logistic curve then, I'm going to delete the top, instead of being a linear line like that, is actually a curve that looks like this. in some cases, you'll still get pi, predictions of the probability of y being 1. You'll get them in a kind of close to a linear regression fashion in some areas, but it never generates invalid predictions because of this process of converting the probabilities into odds and then log odds. The logistic regression is a linear regression in the log odds. And by transforming it from there back into the original space, where y can be 0 or 1, we get a model that correctly predicts probabilities within the range of 0 and 1, always. Now, we're at our time, so there's a little bit more of subtlety with the logistic regression I'll have to get to next week. But if you do the reading, you'll be able to understand sort of more about the log odds and logistic regression. But the main point is that the linear probability model works just by doing linear regression on the binary outcomes. But the logistic regression says, hold on, I'm going to do a couple more transformations, do regression on that, and then turn everything back to the original. It still makes predictions that can be thought of in terms of probabilities, that the outcome is 1 or 0 based on a Bernoulli distribution. Okay? Now I appreciate that this had a lot of statistical content. And I told you early on in the course that the course is mainly a statistical analytical course. It's not really necessarily about R programming. So this is kind of what I mean. Now I'm not going to ask you to derive these properties or sort of present these things in full, but I'm just providing you the theory to understand what's going on when you use the R code later. On Thursday, what I'll do is I'll cover the concepts inherent in the logistic regression when you use it in R, such as how to make predictions about probabilities and how to generate classifications into 0 and 1, such as using the workbook's example of long weights. Okay? So with that, I'll let you go. Make sure to do the next reading early, and we'll be in touch on Thursday about the code. Great. I'm going to stop the recording now.